Hello, in this video we will learn how to solve differential equations in Python numerically. We will do this using the example of a simple pendulum. So I'll start by deriving the differential equations of motion for the simple pendulum. If you don't know how to do that yet, that's fine. You'll be learning that throughout the dynamics course. I'll do the derivation quickly. We'll obtain the equation of motion, and then I'll explain how we'll put it into a numerical solver in Python. So let's first consider a simple pendulum that's a mass m extended by a light inextensible string or cord of length L. And gravity is acting vertically downwards in this case. So first what I do to derive the equations of motion, I'll set up my basis. I'll use the polar basis. This is my origin, ER. How do I set up E theta? Well, let me write a fixed basis. I'll do that. Fixed basis. So then my E theta unit vector is this way. Again, if you don't know how to do that yet, that's totally fine. We'll be learning this throughout the semester. Okay. So then I've set up my basis. I'll draw the free body diagram of my mass M. The forces acting on it are the tension along the cord and the weight. So then the tension is along minus ER and the weight is along EX. Okay, and I can remember the relationship between the fixed basis and the rotational basis, the polar basis, that ER is cosine theta EX plus sine theta EY, and E theta is minus sine theta EX plus cosine theta EY. So when I write my balance of near momentum, the balance of forces is equal to the mass times the acceleration. Then that will give me the minus, or the tension force minus TER plus mg EX is equal to m. The acceleration in polar coordinates of this pendulum of constant length is going to be equal to, well, in general in polar coordinates, the expression for the acceleration is A is equal to my r double dot minus r theta dot squared ER plus r theta double dot plus 2r dot theta dot E theta. So where r is the length of the position vector from the origin to the particle. In this case, this length is constant. So then these two terms drop out and I'm left with minus L theta dot squared ER plus L theta double dot E theta. So then in the equation of motion, I'll get minus L theta dot squared ER plus L theta double dot E theta. Okay, very well. Then I can project the equation of motion along E theta, and I'll get that this term is gonna away, the tension term is gonna go away. I'll get mg x dot E theta is equal to m L theta double dot. Well, what is Ex from dot E theta? From here, that's equal to minus sine theta. So I'll get m L theta double dot is equal to minus mg sine theta. Mass and the mass cancel out. Theta double dot plus g over L sine theta is equal to 0. That's the differential equation governing the motion of the pendulum. Again, this pendulum has 1 degree of freedom, that is the angle theta. So once we figured out theta as a function of time, which is the solution of this differential equation, then basically we know the motion of the pendulum. Okay, so now that we've gotten the differential equation, the next step is we want to input it into a numerical solver. So again, the equation is theta double dot plus g over L sine theta is equal to 0. So usually the numerical solver we're gonna use is gonna be use the Runge-Kutta method, numerical method. to solve the ODE. I'm not gonna go into the details of the numerical method, but what we need to know is that the numerical solvers in Python, they need a system of first order differential equations to solve. So this is a second order differential equation because we have a second derivative of theta. We're gonna need to transform that second order differential equation into a set of first order differential equations. So that's important. So we need to transform the second order differential equation into a set of first order differential equations. Okay, second order ODE, that's an order differential equation into a set of first order differential equations. And that's the procedure to do this is that usually I'll take my variable, say x1, and I'll set it equal to theta. I'll take my other variable x2 and I'll set it equal to theta dot. And then I'll find differential equations for these terms, the x1 and the x2 terms. So let me see. If I differentiate x1 dot, that's gonna be equal to just x2. And if I differentiate x2 dot, this is theta double dot. So basically from this equation, that's equal to minus g over L sine theta, but theta written in terms of x1 and x2 is x1. So then my two first order equations in x1 and x2 are these. Okay. So at this stage, I am ready to input these equations.
In the previous video, we derived the equations of motion for the simple pendulum. We basically got one second order differential equation that we rewrote into two first order differential equations. Here they are in terms of x dot 1 and x dot 2. Right now, I want to solve these equations in Python. I'm using VS Code as my editor, but you can use any editor you'd like. You can also use some online editor where you don't have to download any kind of anything on your computer. So we don't really need to memorize all the functions to be able to solve the differential equation. What I'm gonna do is I'm gonna prompt ChatGPT to help me solve kind of any simple differential equation in Python, and I will edit it to be able to solve this differential equation that I have. So let me just ask how to solve a differential equation in Python. Okay, great. ChatGPT gave me a simple example. This is the differential equation they're solving with the initial condition, and that's how they solved it. I'll copy that into my code, and I want to edit it to be able to solve this differential equation up here in the comments. Okay, so importing NumPy, importing SciPy, this is going to help me integrate, and matplotlib to plot. So this is my ODE here. It's dy dt is equal to ty. So what I'm going to do is I'm going to change that. I'm going to say that that's a dx dt. Where x1 is equal to so x1 dot basically is equal to x2, and x dot, let me keep the notation that I have up there, x1 dot is equal to x2, and x dot 2 is equal to minus g over L sine x1. Well, x, that's x2, and that's x1. So here x is an array. I'm gonna have to use mp.sign, the numpy package, and then I need to tell the function what g and l are. So let me define those. G is the gravity, 9.81 using SI units. L is the length of the cord of the pendulum, and that's say 1 meters. Okay, so now these are global variables, so I could choose to input them into the function this way, or I don't think I need to really. So what I'm returning here is I'm returning the differential equation, which is the derivative of this x array, which is gonna be x dot 1 and x dot 2. I'm not sure if I should return these as an array like this. I will try, and then I will see. Okay, awesome. So this is the differential equation that's being solved. I will see about this array thing. It might not be necessary. We will try it without the np.array, and then we will see what happens. Okay. Great. Okay, one thing I have to be careful of is in Python I don't use parentheses, I use brackets to index a variable. Okay. And then we define the time span and the initial condition, so we're solving between 0 and 5 seconds. Okay, that's fine. I can keep that. Then the initial conditions, these are initial conditions for x now, and I have two values because I have x1 and x2, x1 representing theta and x2 representing theta dot. So if, for example, this pendulum starting from rest, then theta, well, whatever, theta is pi by 4. And we're starting from rest, so theta dot is initially 0. Okay, great. And then we want to solve this IVP dt, that's dxdt, that's the name of the differential equation. T span is the same, x0, and I'm solving at these specific points. So the time goes from 0 to 5, and I have 100 kind of time instances, and this plots the results. So solution.t gives me the time, solution.y0, I'm gonna call this x0. Oh yeah, in Python I indexed from 0, so that's gonna be 1 and 0. Okay, cool. So x0, that should give me theta, so let me just be more specific. Theta is equal to solution.x0, and I'll replace this by theta, and theta dot is gonna be equal to solution.x1. Okay, so basically what's happening when I run the code just to this point on the debugger, oh, maybe I should have kept the y. Okay, now I'm gonna run again. Okay, so basically if I look at the debugger, solution is the solution of the ODE, so I'm gonna kind of output what the solution is, or see what the solution is. It's an object that has the time array and the y array, and the first kind of subarray in this, the first row, is gonna be theta y0, and the second row is gonna be theta dot. Okay, so that's theta is outputting that first array, and theta dot, theta, oh, they didn't run that line yet. Okay, now theta dot is outputting that second array. Again, the initial condition for theta dot was 0. I'm starting from rest, so the array starts at 0. Here, 0. Okay, very well. Let us plot the result. So that is gonna be theta as a function of time. My label is gonna be theta as a function of time. That's just a fancy way to output the simple theta. Okay, I'm gonna x label is time, y label is theta. Okay, the title is solution of pendulum motion. Okay, cool, and I'll stop and I'll run this code and I'll see what I get. Okay, wow, so this is how theta is changing in time. I did not output this well. Okay, let me run again. That's still the old plot. That's the new plot. Okay. So that's theta as a function of time from 0 to 5 seconds of the simple pendulum. The maximum value is going to be equal to pi by 4 because the pendulum starts from rest at this point. Okay, stay tuned. In another video, we will try to animate the motion of the pendulum. I actually done that. This is what we want to get. Some simple, very simple animation of this motion. Stay tuned.